advocated for it. Okay, so yeah, 5 minutes. See you in 5 minutes.
Okay.
I think this is her PhD work. Currently, she works as a postdoc at University of Copenhagen in Denmark. And for more details of introduction, please go to her LinkedIn account to look for more details. And then with that, I will give the rest time for Elsa. So it's great that at least although we start a couple of minutes late, but it's better late than never. So with that, Elsa is going to give a talk for the next 30, 40 minutes, and then we are going to have some interactions. So Elsa, please.
Okay, thank you very much for inviting me. I'm really happy to present my PhD work. So yeah, most of this work was done, carried out at IPGP in Paris, even though now I work at the University of Copenhagen. So in this study, we use calcium isotopes to try to understand the origin of carbonatites as a novel tools. So carbonatites are rare igneous rocks that contain mostly carbonate minerals and almost no silica. They are often associated with silicate rocks, but they are very different from them. There are 4 types of carbonatites found on Earth. The calciocarbonatites, which represents the most common carbonatites we found, and which represents calcite carbonates. There's also magnesio-carbonatites, ferrocarbonatites, which are minor, and natrocarbonatites, which represent the modern carbonatites, as the only occurrence of natrocarbonatites is produced from the only one active volcano that produces carbonatites. And this volcano is Oldonyo in Tanzania. And in this image, we can see the white color lava flow here, which is a solidified lava flow. And this white color reflects the carbonate minerals. Since their discovery, their origin is highly debated. Either the mantle source of carbonatites has an average carbon content, and then to produce carbonatite, a low degree of partial melting of the mantle is needed in order to produce a melt that is enriched in incompatible and alkaline elements. This low degree of partial melting produces then an alkaline magma saturated in carbon dioxide. And this would induce a liquid immiscibility from a carbonate phase to a silicate phase. And we'll have the coexistence of carbonatite magma and silicate magma. Another hypothesis is the extreme fractional crystallization of apparent silicate magma. In these two hypotheses, it's in good agreement with the fact that most of our carbonatites associated with silicate rocks. Another hypothesis is that the mantle has a high content of carbon, and it's this high content of carbon that can explain the occurrence of carbonatites, which contain mostly carbonate minerals. This high content of carbon can be explained by two reasons: either the accumulation of primordial carbon from the deep mantle, or it represents a recycled carbon through the subduction of oceanic lithosphere. Moreover, as the only occurrence of natural carbonatites is actual and is present in all the Nyolangai in Tanzania, and as all calciocarbonatites are older, there is no modern calciocarbonatites. Some authors, and especially Keller and Zetsafe in 2006, have suggested that calciocarbonatites derived from natural carbonatites by the alteration that will substitute sodium by calcium. So the idea of this study was to use calcium isotopes in order to trace the origin of calcium in these rocks, and which will correlate with the origin of carbon in these rocks. So our main questions are: does the calcium in the calciocarbonatites derive from alteration of the modern natural carbonatites? Other word, what is the origin of calcium in carbonatites? Can it come from a mantle source, an average mantle source, or does it have to imply a recycling of marine carbonates in the mantle source of these carbonatites through subduction processes and transfer in the mantle? So for that, to study to tackle these questions, I studied calcium isotopes. Calcium has 6 isotopes, including the major isotope, which is the 40 calcium. And I'm interested in knowing the abundance of the different isotopes. For example, here, all the data I will present is mainly about this notation, delta 44 over 40 calcium, which represents the abundance of the 44 calcium over the 40 calcium isotope of a sample normalized to a standard and in per ml notation. This standard is a calcium carbonate, and it's the international standard we use for these for the calcium. So the calcium isotopic fractionation has been widely studied for low temperature processes, because at low temperature we see more fractionation. It's more easy to fractionate calcium isotopes during processes. And here, for example, it's a compilation of the calcium isotopic composition from Gussel et al. 2017 of different reservoirs, and you have most of the reservoir here come from low temperature process, such as atmospheric, soils, waters, vegetation, and low temperature rocks. And we see that for all these reservoirs, we can see a wide range of calcium isotopic composition. And if we compare to the high temperature rocks, such as basalts, volcanic rocks, granite, and others, we see that they present a narrow range of calcium isotopic composition. So that's why calcium isotopes were less studied in high temperature chemistry. And now that we have a recent development of mass spectrometry analysis, we can now have better precision and analyze even smaller calcium isotopic fractionation. And so now we study more and more calcium isotopes in high temperature chemistry. But all this aspect of calcium can be also used as a tracer of recycled components, because as I said, during low temperature process, such as surface processes, we would expect bigger fractionation compared at high temperature. the theory of isotopic fractionation. And here I compiled data from my PhD for the volcanic rocks and the carbonates that come from literature. And we can see that the carbonates have a wider range, like I said, of calcium isotopic composition, but also they are enriched in the lightest calcium isotopes because they are negative, 4440. They are enriched in the lightest calcium isotopes compared to the bulk silicate earth estimates, which is similar to mantle rocks, such as peridotite, basalts, and archean comatites. So the idea of the fact that carbonates are enriched in the lightest calcium isotopes compared to typical igneous rocks, then if the mantle source of some igneous rocks contain recycling carbonates, we could see it with the calcium isotopes. So it has been used for the first time by Wang and al. 2011, this calcium isotopes as a tracer of carbonate recycling. They analyzed Hawaiian tholeiites, and they show that they span calcium isotopic composition from the VSE value, which is the value of the plume, to lower value at 0.6 per mil. And they see that this calcium isotopic composition correlates with the radiogenic strontium. Radiogenic strontium, as seen as the 87 strontium over to 86 strontium ratio, is used as a tracer of recycled components since a long time ago, because carbonates are enriched in radiogenic strontium, which is the 87 produced by the disintegration of rubidium. And also, there's other studies that show that during the subduction processes, fluid are expelled from the slab during dehydration, because it goes to the mantle at higher temperature and higher pressure. And during this expelled, John et al. 2012 have analyzed high temperature metamorphosed oceanic lithospheric rock, and have showed that the vein containing these rocks, which represent metasomatized minerals that are metasomatized by the dehydration, by the fluid that are expelled, these veins are enriched in the heavier calcium isotopes. So they suggest a model where during the expel of the fluids during the dehydration, when the slab goes in the mantle, the fluid will fractionate, this dehydration process will fractionate the calcium isotopes, and the fluid will be enriched in the heavier calcium isotopes, which would result in a slab that goes to the mantle and will be recircled to be enriched in the lightest calcium isotopes. So the idea of this study is to use calcium isotopes to trace the origin of carbonatites, and because we think that it can also trace if the carbonatites are formed from contribution of recycled lithosphere. So I studied more than 50 carbonatites and associated silicate rocks. These rocks are represented by the red square here. They come mainly from the rock I studied, mainly from Africa, Europe, Greenland, and Brazil. There are different types. I have the calciocarbonatites, ferro, magnesio, and also the natural carbonatites, which are here because they come only from Tanzania. There are carbonatites that come continental settings, but also two come from oceanic settings. And they span age from 3 billion years ago, represent the oldest carbonatites found on Earth, to the present day, which represent the natural carbonatites. So here are the main results of this study. Here you have the calcium isotopic composition of the carbonatites I studied relative to their age. And here we see that most of the carbonatites, and these are only calcio, ferro, and magnesio carbonatites, they are all enriched in the lightest calcium isotopes, compared to the Earth's mantle, which has a bulk value of 1 per mil. And these carbonatites have an average value around 0.3 per mil, which represent the first igneous rocks that have this calcium isotopic composition. So this enrichment in the latest calcium isotopes does not correlate with ages or the realization of these samples. But there's something interesting here is we see that the natural carbonatites, which represent the actual carbonatites we can see, they are not as enriched as the other carbonatites, and also they're very close to the Earth's mantle and to the basalts, the typical basalts we measure, because they're around 0.7, 0.8 per mil. So these observations question ourselves, how can we explain that the calcio, magnesio, ferrocarbonatites are lighter in calcium isotopes compared to the BSC, the biosilicate earth value, and also why they are different from the Lengai natural carbonatites. Well, to explain the arrangements in the lighter calcium isotopes in igneous rocks, there's different processes. So it's good to evaluate all the processes that can explain this enrichment. And the first process that is easy to think is maybe it's only due to alteration. It's post-eruptive alteration. So maybe the rock is supposed to be like the BSC value, and because it has been erupted a long time ago, it has been weathered and altered, so the composition might change. So we're going to test, in the following, I'm going to show you the test to test if it's due to secondary processes. For this case, it's interesting because it could explain that natural carbonatites are modern and calciocarbonatites are old. And so maybe all the carbonatites were erupted as a natural carbonatite, but they were all alterated and they were transformed to calciocarbonatite. And the substitution of sodium by calcium during the alteration might explain the arrangements in the latest calcium isotopes for calciocarbonatites. This is an idea. Another hypothesis is to say that the enrichment in the latest calcium isotopes is due to mantle processes at high temperature, such as the low degree of partial melting of the mantle that could fractionate, and the fractional crystallization during differentiation processes. Or the mantle source is already enriched in the latest calcium isotopes. And then, in order to explain that a mantle source is already enriched, it might be due to a contribution of recycled lithosphere, as I talked a bit before. So first, in order to test if secondary processes can explain this enrichment we observe, I measured a series of modern Oldonio-Lengai natural carbonatites from fresh to altered. And here you can see from Zaitsev and Keller, you can see the evolution of alteration where you lose in sodium content and you enrich in calcium content. And here you have the fresh, unaltered natural carbonatite. Here you have a first stage of alteration, and this is the final step of alteration where there is no sodium and very high in calcium. And these really look like calciocarbonatites. That's why these authors thought that they suggest that this is the alteration that produced calciocarbonatites. So I studied the calcium isotopic composition of fresh, altered with personite and altered with calcite that are present here. And we see that for all these different stages of alteration for natural carbonatites, there is no correlation with the calcium content. And furthermore, most of these altered and fresh carbonatites have the same calcium isotopic composition. And if we look here, carbon isotopes have been widely used to study the primary field of carbonatites and to study if the carbonatites are primitive or they have suffer alteration or weathering or other different post-eruptive processes. And here, while we see a correlation with the carbon isotopic composition and the calcium content that reflect alteration processes, calcium isotopic composition, which is in the blue dot, does not correlate with carbon isotopic composition. So these results imply that the calcium signature of all calcium carbonatites cannot be due to substitution of sodium by calcium. And that then calcium carbonatites we measured cannot be explained, at least the arrangement of the latest calcium isotopes we observe in these calcium carbonatites cannot be explained by alteration of a natural carbon processes, and this kind of important secondary processes for carbonatites. The enrichments in the latest calcium isotopes can be due to mantle processes. And as I said, most of the carbonatites, they are associated with silicate rocks. And these silicate rocks are a bit peculiar. They are alkaline silicate rocks, so they have low content of silica, and they have high content of alkali. And usually they are around here. And most of the alkaline silicate rocks are represented by phonolites, for example. And to explain the formation of these alkaline silicate rock, there are two hypotheses. One is a low degree of partial melting of the mantle because it will enrich in incompatible and alkali elements. And if the mantle source, there is a low degree of partial melting of the source, then the first mineral to enter the melt will be the clinopyroxene, which are here. The first calcium-bearing mineral will be the clinopyroxene. And while clinopyroxene are enriched in the lightest calcium isotopes compared to orthopyroxene and olivine, they still have a value that is very different from the carbonatite value, which is more around here, 0.3 per ml. So even if we have a melt, because it's a low degree of partial melting, a melt that is enriched in clinopyroxene, it's not sufficient to explain the value we obtain for carbonatites. So maybe this value we obtain, the 0.3 per ml, and so this enrichment in the latest calcium isotopes, maybe it can be due during differentiation and during fractional crystallization. Some studies, at least 3 or 4, have trying to understand if calcium isotopes fractionate during the differentiation processes. And here it's an example of a study of the Kiloiki lava lake from Zingenthal 2018 that showed that during differentiation, which all these samples are reflect, there is no correlation with the MgO content, implying that there is no calcium isotopic fractionation during the fractional crystallization in Kiloiki lava lake, which is a tholeiitic silicate magma. But carbonatite magma have lower temperature as tholeiitic silicate magma. And as I said before, because it has lower temperature, it could induce bigger fractionation. So we have to try to see if maybe it's during the differentiation of the magma and the fractional crystallization that we can explain an enrichment in calcium isotopes through this process. Here I have presented 3 complexes, tubertalic Singertats, which are 2 in Greenland, and Brava, in Brava Island in Cape Verde. And here all the colors reflect one complex. And what I can roughly see that there is a correlation between calcium and magnesium content. So there is an enrichment in calcium content during the evolution of the magma. If we look at the calcium isotopic composition, we see no correlation at all. So it will imply that for these same complexes, because they come from the same mantle source, if they evolve during fractional crystallization, if they don't see any difference in the calcium isotopic composition relative to MgO, to magnesium content, which would imply that fractional crystallization does not induce calcium isotopic fractionation. So we can think as another process, because I said that there's one hypothesis would say that carbonatite and silicate magma, they coexist together, but in a liquid immiscibility phase. Maybe during this liquid immiscibility, they could be transfer of calcium to a phase to another, to the silicate phase, to the carbonate phase. And though it has never been studied for this kind of liquid immiscibility in carbonatites, Moigny and Fuji 2017 have calculated, using ab initio calculation, the fractionation factor for calcium for different aqueous species. And I've used their fractionation factor as a first order, because of course it's not the same environment, but as a first order, I was trying to see if we could expect fractionation during this transfer of calcium. And here we see that the remaining of calcium in the silicate phase, where there's less and less calcium in the silicate phase, we see a fractionation depending on the different species. These are all the species I used for the calculation. Depending on all the species, we see there's a fractionation. But if we look at the extent of the fractionation, we see it's very small. It's less than 0.1 per ml. So it would suggest that it's hard, even if it's at first order, it's hard to induce a big fractionation through this process. Overall, there's, like the study of Zheng and out 2018, there's one study from Chen in 2019 that showed that it's very difficult to fractionate calcium isotopes during partial melting and fractional crystallization. And they show for a lot of different rocks where they reflect either fractional crystallization and partial melting. They don't reflect calcium isotopic fractionation during this process. So the idea is to say that, well, this enrichment of calcium isotopes we see in these carbonatites, they cannot be explained because it's a huge difference from the BSE value to the carbonatites value. We cannot explain it by this process and also the secondary process, like I showed before. So it would mean that the enrichments in the lightest calcium isotopes come from the mantle source. And so it's the mantle source that is already enriched in the lightest calcium isotopes. And this could be related to recycled carbonate fingerprint. But in order to go further, we try to analyze also associated silicate rocks, because associated silicate rocks to the carbonatites, for most of them, they come from the same source. So if we also have, if we also study the associated silicate rocks, we can then have a better understanding and better insights of the mantle source. So this is just an image of a carbonatite dike in a silicate rock. So on the occurrences of carbonatites in the world, there's only 100 that represents carbonatites that are with no silicate rocks. But most of them, they are associated with alkaline silicate rocks. For example, phonolite syenites, nephenonites, isolites, which are all these associated silicate rocks we can find in Lengai, the Tanzania volcano that produced the natural carbonatites. But also we found these association with most of the carbonatites. So I studied silicate rocks for 3 complexes. Brava Island in Cape Verde, Tubertalic and Sigertat in Greenland, which represents the oldest carbonatite, and in Brazil, Jacupiranga. Here it's just calcium isotopic composition of these carbonatites that we see are not does not really correlate with the carbon isotopes, which would say that the calcium isotopic has a primary signal. So this is the result of the carbonatites and the associate silicate rocks. And here it's striking. You can see that the associate silicate rocks, of course, they have low calcium contents because they are not carbonatites, but they are also does not present the same enrichment of the latest calcium isotopes. And if we look a bit more closer, we can also see that there is a correlation where a decrease of calcium content reflect an increase in the calcium isotopic composition, so an enrichment in the heavier calcium isotopes. So this can be mostly due to differentiation processes, and we can see it in this graph where we have the content of sodium and potassium, which are alkaline elements and which represent differentiation tracer. And here we can see correlation, nice correlation for Sigertat and a bit less obvious for the other complex, but because we don't have a lot of samples also. But here we can see it a bit better with the MgO content, which reflects differentiation process. And what we can see is that the lowest differentiated silicate rock, which is fluorite, for example, they have a calcium isotopic composition which is close to the carbonate associated silicate rocks have heavier isotopic composition. So the idea is, well, the lowest differentiated represent the most the metal source, and these samples have the same composition of carbonatites and the same, if we look here, they have the same contents of carbonatites here. Of they have the common source would have this content of calcium and this calcium isotopic composition, which we can see it here. So this metal source is then enriched in the lighter calcium isotopes compared to the BSE, the burnt silicate earth, and it's roughly 10% of calcium, of outside calcium, and calcium isotopic composition of 0.3 per ml. So this could reflect this source that is enriched in calcium compared to the BSE and in the lightest calcium isotopes could reflect carbonates, marine carbonates, which also are enriched in calcium contents and in the lightest calcium isotopes. So we did a simple mass balance, and with a starting material of a mixing of BSE value to calcium composition of to recycled material from subduction, and with three different, because this is not very known, so we use three different composition, and this mixing could explain the isotopic calcium isotopic composition of the carbonatites by adding less than 10% of recycled carbonates in the metal source of carbonatites. Then we can still wonder why natural carbonatites are different from calciocarbonatites. Well, there's a study of Fischer and al. 2009 that have analyzed all the new Langai gases and have estimated the carbon content in the metal source of natural carbonatites. And they have shown that the natural carbonatites have present no enrichment in carbon content compared to the average carbon content in the metal, and which is in agreement with the calcium isotopes, because natural carbonatites have composition that are close to the BSE value. So it will mean that natural carbonatites does not represent a recycled, does not have contribution of recycled material in the metal source, but the other carbonatites they do. And the difference of their chemistry, and mainly the abundance of sodium can explain this. So to conclude for this study, we have analyzed a lot of carbonatites from different parts of the world. They all present an enrichment in the lighter calcium isotopes, and are very different from any other igneous rocks. And their mantle source is also enriched in calcium content. We also showed that differentiation processes occur only for associated silicate rocks that deplete in calcium contents and deplete in the lighter calcium isotopes. This this conclusion has great implication, because if these carbonatites are formed from contribution of recycled material rich in carbonates, it would imply that the onset of plate tectonics has at least begun 3 billion years ago, because the oldest carbonatites we analyzed is 3 billion years old. So with that, if you want more information, the paper just was published 2 months ago, so I can you can read the paper if you want a bit more information, and I'm happy to take any questions. Thank you.
Okay, thank you very much, Elsa. So it's time for questions from the audience. Feel free to open your mic, ask questions, or just type questions if it's convenient for you to ask questions. And it's okay if you ask questions in Chinese, and I could do the translation. So go ahead.
Thank you very much for the lecture. I was wondering, did you consider the effect from beta thing that comes from potassium 40 can give additional calcium 40? So did you consider any effects from this reaction?
No, because I don't really just have to look for the because I'm using where is it? I'm using not a TIMS, I'm using MCA-TPMS that has a plasma source, and the plasma is an argon plasma. So I don't actually measure the 40 calcium, because argon has the 40 mass also. So I only measure 42, 43, 44, and I'm renormalized measuring to have the 40, because in the literature they mostly show this notation. So I cannot see the there is no, because I don't measure the 40 calcium, there is no radiogenic calcium produced from potassium. And for people who do measure the 40 calcium, usually they always correct from the radiogenic input. So it's not really a problem.
Thank you very much.
Okay, when you ask questions, please let us know your name and your institution. So Natasha, could you restate about that?
My name is Natasha. I'm from Lomonosov Moscow State University.
Next question, please.
Hi, Elsa. My name is Wei Dai from CUG Wuhan, and I have a question. And before your article has published, another research which is done by Banerjee, which is an Indian researcher. He also measured a carbonatite complex, and his result is quite different from yours, I think. Do you have any?
Yes.
Do you have any ideas?
Yes. So the carbonatites, the complex where these carbonatites come from India is Ambadongar, which is a famous complex, and this complex has been hydrothermalized by the fluids that are enriched in strontium and calcium, and they measured. I don't remember, but a couple of carbonatites in this complex, and they see variation. They see light around 0.6, so not very light, 0.5, 0.6, and me it's more 0.3. But I have 0.5 also, because it's a small range. And then they show carbonatites who are enriched in heavier and even more enriched than any other basalt or any other igneous rocks. And also they measure the radiogenic strontium. And in these carbonatites, which are rich in the heavy calcium isotopes, they also have very, very important radiogenic strontium. And this is exactly the same composition for calcium and strontium in the fluorspar deposit that is in Abondongar, and that could have alterated the carbonatites. And these carbonatites are heavily alterated by this process. So I think that these carbonatites might more for the calcium isotopes might more show the alteration process or post-eruptive process through hydrothermolysis. So maybe it's not a primary signature. That's how I could explain the difference.
All right. So so the sample from Langai and may also have the similar processes.
Similar as Ambadongar?
Yeah.
Well, so most of the natural carbonatites we analyzed, they were collected just after the eruption. So they were not alterated in the surface, and they don't present if they are alterated before through metasomatized processes by hydrothermolysis or like warm fluids, hot fluids. We don't see any fluorspar deposit like in Ambadongar, and so we don't think it could be due to this process. Maybe there's more work to be done for that, but there's no evidence of this kind of process there. So,
All right. Thank you.
Okay, next question, please.
so when you mean fresh, you mean not alterated, or? Well, most they show sign of alteration, and I can find it here if you want. There's a paper, very old paper, that says that this is carbonatites from different places, and you see that this is the primary field, which is the mantle value of carbonatites without any post-eruptive alteration. And you see that some carbonatites that are not, that are away from this box. This is a Langai box from a Taylor, from a very famous paper. And some of these carbonatites, they show increasing of delta 18O with no much increasing of carbon isotopic composition. And it has been, by this paper and other papers later, it has been seen that it's due to alteration. And in fact, most of the carbonatites we analyze, they show this trend. So in mine, I think maybe 10% are in the box, and all the others, they are close to this value, but it does not, because so it will alter the carbon and oxygen isotopes, but it will not apparently, like what I studied, it will not alter the calcium isotopic composition. So this is a good tracer to use to test this.
Okay, next question, please.
Hi, Elsa. Thank you for the nice talk. This is Joyce Sim from Georgia Tech. My impression from previous experiments were that calcio carbonatites cannot actually cannot really form under high pressure based on petrogenesis experiments. So this is like the Lee Wiley paper in 1996 and like Brooker et al. Can you comment on that, please?
Yes, exactly.
How can you reconcile?
So carbonatite liquids, they are not stable at low pressure, so at atmospheric pressure, and that's why all the volcanoes they don't erupt carbonated lava. They only emit carbon as a carbon dioxide. So that's true. It's not stable, and the idea is that if you enrich in carbon the source, then you can have eruption of carbonates and not just carbon dioxide gas. So they tried, I don't remember exactly how much percentage of carbon so calcium, ferro, and magnesium. For the natural carbonatite, for example, it's the high content of sodium, which would be enough to have carbonated liquid stable at low temperature because of the high content of sodium. But for the others, in order to be stable and erupt as carbonated magma, then they have to present an enrichment in carbon. It's one of the ideas to explain this.
Thank you, Elsa. But you're talking about low pressure, right? Like I'm talking about high pressure, so kind of lower mantle kind of pressure.
So before the partial melting?
Yeah, so I mean, so I mean, your paper is kind of suggesting that this is coming from the mantle, right? And from what I understand from the petrogenesis of carbonatites, is that high pressure calcio carbonatites cannot really form. That's why I was asking for your comment. Yeah.
Okay. Well, I think it's more magnesium carbonated liquid that can be formed at high pressure. But then I would assume that when they go, because they can be formed at high pressure, but then, well, they contribute in the mantle source, then they can be more enriched in calcium. It doesn't mean it's like a calcium carbonatite liquid. It means only like what I've shown is it has to be 10% of calcium. So it's not that enriched. It's not like a calcium carbonatite composition, but it has to be at least 10%. So it's still enriched in calcium, and but maybe not exactly the same composition as but the experiments they indeed they don't at high pressure, but maybe here I only talk about 10%. So maybe I have to be more specific about that, but maybe it can be enough to be produced. And maybe they'll produce at less pressure, high pressure.
So what you're saying is that it kind of starts off with magnesium carbonatite, and then there's enough calcium to, eventually on the way kind of be substituted or something like that. Okay. Yeah. I don't know the percentages, so yeah, I'm not sure about that. Yeah. Thank you.
Okay. Thank you.
Great. Okay, next question, please. Okay, I think that's so much for tonight or this afternoon for Elsa. Okay, thank you very much for the talk, and also thanks everybody for participating. Okay, for more information,
thank you
please.
for inviting.
Yeah, for more information, feel free to check our Google Sheet as well as Tencent Sheet about the coming talks. Okay, great. Thank you.
Thank you very much.
Have a good afternoon. Bye-bye.
Thank you. Bye.